Thank you all very much for staying on after the most recent Dive Deep section. That was really one of the most moving sessions I've seen here so far. And actually, I hope to extend upon some of those discussions that we had just an hour ago in my talk today. And I promise to leave enough time for us to have some questions, because we're actually going to come around full circle to actually discuss how climate change impacts people. So I am a geological oceanographer. I'm someone who looks at ocean sediments as a way to reconstruct past climates. And in the course of having done that, we've understood how climate changes and how it impacts ancient cultures. And in particular, I work off the coast of Africa. So I'd like to just start with this concept that one of the best places for us to start with this is that climate shapes life from a variety of timescales, from seasons. Seasons pace the cycle of death and renewal. And as we can see here in this image of the terrestrial biosphere, both on land and then in the ocean biosphere shown here in the green, this is the pulsing of chlorophyll on the planet as paced by the seasons. So the planet is literally breathing in and out with carbon dioxide and oxygen. It's a living, breathing planet. And of course, everything that's chasing that primary productivity, including humans, is very much tied to changes in climate. And so with that by way of an introduction, I thought I'd take a preliminary walkthrough of what I think is probably the single best poster child example of how humans respond to climate change. One of the challenges about getting our heads around where we're going to be in the coming decades is that we don't know where we're going to be in the coming decades. We believe we know how to think about it. We think fast and we think slow about climate change. But mostly we think fast about climate change. That is, we're very reactive. We use our fast brains. We respond very rapidly to these emergencies that present themselves. But really, we should be using our slow brains, our very rational thinking about the future. And so this is using the slowest possible brain, actually dialing back deep. In this case, we'll be looking back 10,000 years into the past to see how people responded to what was one of the most profound climate changes that modern humans have ever witnessed. And this is the climate-driven depopulation of the entirety of North Africa, in fact, including of East Africa as well. So we'll have two parts to the talk today. The first will focus on this sort of archaeological connection to climate change and ask the question, how did ancient populations in North Africa respond to past climate change? Then we're going to take that lesson from the geologic past, this kind of history lesson, to think about how climate is changing today, and in what ways what's happening right now and into the future is comparable to that experience, but really how it differs from that experience. So the first way to start with this is a world map that you probably have never seen before. It certainly doesn't look very familiar, but it's really to convey the idea that the North African subcontinent is massive. It's twice the area of the continental United States. It's something that we often don't think about. That's why I included this in my few slides that I use, because it really is truly massive. It includes the United States, all of Western Europe, Eastern Europe, India, and if you want to go down into the tropics, it's China as well. So it's a really massive physical place. And most of it is barren. You'll see here in the northern part of North Africa, that's the Sahara Desert. The Saharan Desert is this massive sand sea that is largely much more evaporative than it gets rainfall. In some places, there's an excess of evaporation of 4 meters relative to incoming rainfall. But you can see that the seasonal cycle that I showed earlier of chlorophyll, that is plants on the planet, move north and south with the seasons. And this is what's known as the African monsoon. So when it goes northward, that's the northern hemisphere summer. That's this time when you're in North Africa when it rains. And then they have a very dry winter season. And it goes back and forth like this season after season. And this is the African monsoon. So this is the pattern of climate change that we see today, or the pattern of modern climate that we see today. But you'll notice that it never really reaches much above that green line, which is about 20 degrees north. That green line is what's known as the Sahel, which can be translated to beach from Arabic. And it really refers to the shoreline of where the well-watered southern tropical regions meet the very dry, hyper-arid expanses of the desert. So this has been true, that position of that Sahel grassland layer has been there for a very long time. But if we dig back into the geologic past, we find that that's not true at all, that this rain belt actually extended much, much further deeper into North Africa. The reason why the rains advanced when we extend back thousands of years into the past, 5,000, 10,000 years into the past, has to do with the fact that the Earth has a wobble to it. The whole Earth wobbles like a top, and the period of that wobble is about 20,000 years. So the way that we had experienced it as humans, if we could speed up the clock, is that as we look at the North Star Polaris, you know that all the other stars rotate around that one star, right? That's the pole star. But 10,000 years ago, our North Star wasn't Polaris. It was a star Vega, or close to it, which is 47.5 degrees in the other direction. That was our rotation axis 10,000 years ago. And so this wobble cuts out a circle in the celestial sphere. It actually cuts out a cone in the celestial sphere. But what that means to people living on Earth at the time is it meant that the summers in the northern hemisphere got about 7% more sunlight than they do today. They actually had a hotter summer, and the winters were exactly cooler by that exact same amount. Excuse me. So what that means for Africa is that it changes the heating over the continent, and it allows the monsoons to move more deeply into the desert regions, where the desert regions are today. So while this is a snapshot, a space photograph of North Africa today, if you could take the space station and fly over North Africa 9,000 years ago, which was the peak of this wet time of North Africa, called the African humid period, 9,000 years ago it would have looked like this. This is an artist's rendition, a very generous one, but it had a couple of things that are very different than today. First of all, there was no Sahara Desert. It was completely vegetated. It was covered with animals that today grace the grasslands of East Africa. Also, it had these lakes, Lake Mega Chad, which is Lake Chad today is very small, but 10,000 years ago was twice the size of New York State. There were lots of other small permanent lakes around the basin. So the question is, how do we know this? And we know this by a lot of archaeological work that's done where scientists have driven into the deserts. And when you descend down the faces of these sand dunes, you'll often find at the base of the sand dunes a paleo lake or a paleo shoreline, where you'll see sticks or a coarse sediment deposit that indicates a paleo beach, like what you'd see in Lake Mead today, for example. And you can actually date that with radiocarbon, and it turns out to be 10,000 years old. And it's not just one, but there are hundreds and hundreds and hundreds of these lakes throughout East Africa. This is actually what one of these things looks like if you go there today. You get these towers called yardangs of sediments that are made of diatoms, these freshwater algae that lived in this lake. You can see the paleo shoreline in the horizon. And if you dig into these sediments, you'll often find articulated vertebrae of Nile perch. These are not perch as in little perch, but these are like 6-foot-long Nile perch with teeth about the size of your pinky that you'll find these in these sediments all the time. So if we go to a place that's this is actually on the western shore of Lake Chad, a site called Gobero. This is a site that where Paul Serrano, actually a graduate of our program at Columbia, who's now at the University of Chicago, he went there actually looking for dinosaurs because there are Cretaceous rocks in this area. But he didn't discover dinosaurs, he discovered human remains. And he actually discovered the world's largest collection of burial sites dating from this time about 10,000 years ago. So you can see those little spots in the middle of the photograph. That's actually their camp. And it just gives you an idea of the expanse, the emptiness of this place. What they find on some of the outcrops are these beautiful engravings of animals, of course, that don't exist there today. You find pictures of crocodile and hippopotamus, in this case a giraffe, indicating much wetter conditions than exist there today. Also at these sites, if you do a little bit of systematic digging, you'll find fish hooks made of bone, you'll find barbs made of bone, wavy line pottery, and these are all sediments that are 5, in some cases 10,000 years old. This is just one of the burial sites. Some of you may have seen this photograph before. It was covered in National Geographic. This is an image of a burial site with a mother and her 2 children laid together, embracing each other, all holding hands, and what they believe, based on pollen, where the bones meet the soil, on a bed of roses, or a bed of flowers, rather. So it's a very advanced culture as well, systematic burial. So our question is, when did this thing happen? When did this wet phase happen, and how did it change? Did it change gradually? Did the modern Sahara Desert, somebody asks you tonight at a cocktail party, how old is the desert? The quick answer is it's about 5,000 years old. The longer answer is it's about 20 million years old. The actual desert itself was established a long time ago. There were these wet and dry cycles going on since that time. We know that we can date the last time that the site was wet by measuring the concentration of this wind-blown dust. This is actually wind-blown dust that's carried by the winds to the west, and that dust actually gets carried out over the oceans, where it becomes ocean sediments, and this is where I come in. Because what I do is I take a ship out, and we'll take cores, sediment cores, long tubes of mud from these margins along the coast of Africa to try to see when the last time was that there wasn't any of that dust. So we take a ship like this. This is actually one of the ships from the Woods Hole fleet that's actually been retired. Sad to say, it's a ship that's near and dear to any oceanographer's heart, the Oceanus. And it's a small but very functional research vessel. When you're out there, it gets a little wet because she lies a little low. But we'll take out a sediment coring device, and this is actually what one looks like here. It actually has a weight of about 1 ton of lead on top and then a long drain pipe below. And you'll have this core. This is a split core here that's shown on the left. You'll notice that the upper part of the core is reddish, and the lower part of the core is kind of gray. The upper part, the red material, is actually the dust that's coming from Africa, and the gray part is when there's less of it. And so we can actually measure this geochemically. And when we do, we come up with this following wiggly line. And this shows this time period from 0 to 25,000 years ago. So it's a long geologic time period. Then it says solar radiation. That's the Earth's wobble. You'll see that 10,000 years ago was the peak of the wobble. That's when the monsoons would have been strongest. Things would have been wetter. And indeed, that's the time we see less dust at that time period. But then as you move up the core, you'll see there's this transition when all of a sudden the dust increases very suddenly within a couple of hundred years. That's the emergence of the modern-day Sahara Desert. So that transition surprised us because the forcing, the thing that's causing it, is very gradual. It's like a sine wave. It's just a regular sine wave. Whereas the response, the climate response, is really, really abrupt, really fast. So one of the interesting aspects of this is that we can now turn to the archaeological record from North Africa and ask the question, how did people who were living in this wet, verdant Eden, Garden of Eden that was North Africa during the African humid period, what did those people do when Africa started to dry up? And we're very fortunate that the Germans and the French have been fighting it out for decades, trying to see who could come up with the most robust record of archaeological history in North Africa. And as a consequence, we have actually a very detailed picture of what's happened at this time. What this is showing is, this is actually the Nile River. You can see the edaphic, or the sort of strip of green that represents where the river water is. And then in the sand seas to the west of that, so to the left of that, are these ancient occupation sites that date back to 5,000 or 10,000 years ago. And what this is laid out here is it's versus latitude on the y-axis, the up and down axis, and then it's time on the x-axis. And so what we're looking at is when people were living in North Africa, early anatomically modern humans, were living in North Africa with animal husbandry as well, hunter-gatherers to start out with, and then sedentary pastoralists afterwards. And then at the time of this red line, which is that shift that we see in this core, off of the sediment core off of West Africa, Africa suddenly dries up, and the people are gone from North Africa. What's interesting, and this is where I'm going to get to, this is an interesting twist to the story, is that right after this drying up of North Africa, and the early human cultures that were living there abandoned the interior of North Africa, an amazing thing happens, which is that the people move. They migrate, which is what we would do if we ran out of water, which is why this is relevant to the last session we just saw. But they move to a very specific place, and a very specific part of our history develops at that time. They move to the Nile. Why do they move to the Nile? Because it's a source of permanent water. And that rise of sedentary, urban, stratified culture along the Nile is the emergence of pharaonic culture. So this climate-driven evacuation of North Africa led to the population concentration along the Nile and the political consequences associated with that. And within a few hundred years are the first pyramids. So during the African humid period, the AHP, you can see these red dots, that's where people were living. And then after the African humid period, you can see they all migrate to the Nile. A team of archaeologists have put together an amazing compilation of all of the radiocarbon dates that have been used to date all of the archaeological sites in North Africa. It was a huge undertaking. This actually happened just last year, late last year. And I wanted to show this to you. It's a little bit of a long exhibit, but I wanted to show it to you because what it's going to show is the intensity of the yellow is the intensity of occupation sites, the number of occupation sites per unit time. That's clicking away at the top. So at the peak of the African humid period, around 6,000 or 7,000 years ago, you can see the entire interior of North Africa was alive and thriving. And then what you'll watch is they move further and further to the south, and then eventually they disappear. What was removed from this analysis is all the action that happened along the Nile, because there's so much action, it just turns that whole part of the Nile like a band of fire. They all move across to the Nile. So what's interesting is that within just a few hundred years, a few centuries after this drying up of North Africa and the depopulation of North Africa, is the rise of the predynastic cultures along the Nile. This is known as the Naqada III period, and it's the time when we see the first evidence for named kings, state formation, the unification of the upper and the lower Nile, and many notable firsts, including, we believe, irrigation associated with this. So there's a very large cultural benefit to this massive climate change. Why did it happen? Because people were taken out of their secure areas, put into a new environment with new requirements, and new culture emerged. It's happened time and time again in many other places of the world. This is just one example where it's something that speaks very much to our own heritage, because most of our own political systems actually draw from this as well. So what I'd like to do is now sort of change gears to go to part two, which is to understand how climate is changing today, why it's changing today, and why I believe it matters to people. So this group here has shown itself to be very well-schooled in current climate change and why it's changing. All of you know that the Earth's temperature has risen just under a degree centigrade over the last century or so. Some of you may not know that actually this year, so far every month this year, it's been the warmest month ever recorded in history. So we've had the warmest 5 consecutive months ever measured in 134 years that we've been keeping such records. If we were to plot just the average temperature for this year of 2015 for what we have now, it would plot up where the number is, where 2015 is. So it's just busted out. It's broken out. We're going to have to change the scale of the temperature plot. So this is something that this is an article that or a link I would all turn you to. I've located it here at the bottom of the image. This is the Bloomberg.com, and this is a plot that shows what is controlling this temperature rise that we see. Is it the sun, which is, of course, in yellow? No, it's not. Is it variations in volcanoes? Well, that explains a little bit of the coolings that we see in there. If we look at orbital change and solar and volcanic all together and add them together, it doesn't explain the current warming, but it has some of the features are common to this. Well, let's look at some other things. Is this deforestation? We are deforesting the planet at a record pace. No, the land use isn't doing it. Is it ozone? Is it changes in the ozone in the atmosphere? No, that's not causing the warming. Is it changes in aerosols? Aerosols actually have been cooling the planet. Is it greenhouse gases? A lot of it is greenhouse gases. What's amazing is when you pull all of those factors together, natural and man-made, put them all together, you get this plot here, put them together, and you get a beautiful fit. What's more impressive is if you include the volcanoes, which is responsible for those sharp coolings, you get an even better fit. So for anyone who is needed, wanting to see sort of visual evidentiary proof that climate change has a very human fingerprint on it at this moment in time, I urge you to take a look at this link. It just came up last week. So the planet is on the move. Not only is it warming about a degree, but the ocean temperatures are rising at a marked pace. Sea ice, of course, is decreasing. Glaciers are decreasing. These are all things that I'm sure you're familiar with at this point. But what's interesting, certainly from my perspective, because this is what I do, but is to say how unusual is today relative to the distant past. The challenge is that we really don't have thermometer records that reach back much more than a century or two. Records from, let's say, Stockholm might go back 250 years, but those are the longest temperature records that we have. So to get back deeper in time, to go back 200 years, 300 years, 500 years, or a millennium even, we need to do something different. And this is actually what my group at Columbia, or what our group at Columbia excels in. We use tree rings, because tree rings are very faithful records of temperature or rainfall. We also look at corals. This is actually my college roommate drilling into a coral. It's Brad Lindsley drilling into a coral off of Fiji. This is our ocean coring work in below, and we also use ice cores as well. These are all what we call annually resolved archives of past climate change. And they tell us, they are these sort of quiet sentinels that have been recording climate change in eons past. And we can use that as a way to ask the question, how weird is today relative to the last 1,000 years, let's say? So this group of 78 researchers representing 24 different countries just came up with this result earlier this year. And they came up to the conclusion that the red line is the instrumental record. The blue line is reconstructed from the corals and the ice cores and the ocean sediments. And the take-home point is a pretty simple one. Today is weird. It's the warmest temperature that we've had in the last 1,000 years. But this isn't really the strangest part of it. What we can now do is we can ask the question, well, how much warmer will it get, let's say, by the end of the century? And that number is debated. It comes with a lot of assumptions about our behavior. What kind of economy will we pursue? Will we pursue carbon capture and sequestration? Will we pursue a more carbon-intensive or a more carbon-efficient economy? These are all assumptions that we have to make about the future. But we can come up with different scenarios. And those scenarios give us different results. All of them are warmer. But when you take the average of how much warming we're expected to see, it's something like about 3 degrees centigrade warmer by the end of this century. So that's a hard number to get your head around. It sounds like a lot, but we experience 20 degrees or much more than that even swings in temperature in a day, certainly between seasons. So what I'm going to do is now compare this record, the instrumental record and this paleo record that I was just telling you about of the last 1,000 years to what the next 100 years will look like and put them together on the same scale. That's what 3 degrees looks like on top of where we are today. So we really move into a different world. And it's, the shock that I heard in this room is the shock that I had when I made this figure a long time ago. It's remarkable. And it's something we have a very high degree of confidence in. But one of the take-home points that that comes to me on a daily basis is that very few of you in this room, and I would argue none of you in this room, really have any personal connection, any deep personal connection to 2 or 3 degree temperature warming. That's a hard number to get your head around. It's the whole world warming by 2 or 3 degrees. What does that mean? If you live in Minnesota, that's not a bad thing. If you live in other parts of the world, it's kind of a little alarming, but it's nothing that's going to change your behavior. It's nothing that's going to make you want to go home and either vote differently or act differently or raise your family differently. And so I had this moment. I had an interview on CNN with Christiane Amanpour, and we were talking about climate deniers or something like that. And I had this moment. You can actually see it. It's on YouTube. There's a moment where I'm staring at my shoe, and this idea hits me. And the idea is the following, which is that what we can do as climate scientists, and especially what we can do at Columbia, because we've got one of the largest groups, the Lamont Doherty Earth Observatory, where I work, has a staff of 600 with 250 PhD scientists. More than half of those are climate scientists. So these are people we could mobilize to work on this problem. And the problem is the following, which is that I don't believe that talking about fear into the future, that's certainly not the way to motivate anybody. Talking about struggling polar bears or whatever element of fear you want to use is not the way to push any of us to move along. Similarly, just talking about 2 degrees centigrade or 350.org or these metrics, these bars, they don't really mean anything to us personally. And what we need to do is have a conversation at the dinner table, in my opinion. And the only way we can have that conversation at the dinner table is to talk about stuff that matters to us. What matters to us? It's the security of food, water, shelter, and sustainable energy solutions. And so our idea, the thing that we're pursuing at Columbia right now, is to mobilize our scientists using a novel funding approach where we have our scientists who are specialists who generate the kind of data that you've just seen and have them move their energies a little bit off to one side and focus on things that matter to us. And I'll just give you some examples. There's actually 3 new papers that came out just in the last 6 months, and I'll show you just some results here. Some of the authors of that work is here tonight. So how will climate impact crop yields and grain prices? These are things that matter to us because this is what controls our food supply and what we pay at the store. Ocean productivity and health. We don't live in the ocean, but by God, we get 20% of our protein from it. Freshwater availability, we just spent an hour and a half talking about that at the previous session. It's fundamental to our sustainability. I don't need to tell anyone in the West that. Extreme weather, that's the human face of climate change. Hurricanes, tornadoes, destructive storms, these are things that people care deeply about. How does climate impact geopolitical stability? This is actually the military, the US military is deeply interested in this. Regardless of what our government has to say, the military is moving along this full steam ahead. Sea level and coastal assets. This will be the most expensive footprint of climate change. Fortunately, the ice sheets melt slowly, so it's not something that's likely to happen strongly within our lifetime, but they will be certainly things that we have to take into account. I'll just give 3 examples of some work that's been done at Columbia on this, but it doesn't really matter that it was done at Columbia. It could be done anywhere. This is a paper that came out by Schlenker and Roberts. There was a follow-on paper that came out with David Lobel just a few weeks ago at Stanford. If you look at the 4 major commodity crops, all of them have this very strong sensitivity to extreme temperatures. So it's not so much the mean temperature. What's the single largest determinant for crop yields globally is the occurrence of killing temperatures, where you have extended hot temperatures in excess of 29 degrees centigrade for 5 days or longer. And when you have that, it can kill flowering times, it can dwarf the crops. And you can see the yield, the shoulder on the yield, the diminished yield, and notice that this is a log plot. So this is a cliff, if you will. So what happens with global warming is that the extremes happen a lot more frequently. The extreme warmth becomes much more frequent. Consequently, the take-home is that crops will be affected. This is actually work done by my colleague Sonia Dyerman, who actually gave a talk earlier this morning. She's been a hero at Lamont working on how the ocean's microbes, so every other breath that you're taking in this room now comes from these ocean microbes. See that green plot that's in there, that big plot of green that's in the middle of the tropical seas? Those are these blue-green algae. Those are these blue-green microbes. Advancing to the year 2100 in this simulation, it all disappears. This is the core of our planet. This is the base of the food chain. This is what's feeding the protein that we eat. This is our sushi bar. This paper is just coming out, I believe, next week. Lastly, this is, again, circling back to our talk that we had, or our session that we just had. This is actually some work by Ben Cook that came out earlier this year, where they looked at multi-model ensembles. That's a lot of buzzwords for, they used every climate model that's available in the globe, ran them all dozens and dozens of times for hundreds of different simulations, averaged all those results together, and you get these wiggly lines for the American Central Plains or the American Southwest. This plot goes back to 1,000 years ago. How do they do that? With tree rings. So we have tree ring records of past climate for the entire continental United States going back at least 1,000 years. And you can see there have been wetter times and drier times in the past. What happens, you'll see this big steep dive that happens in the contemporary era, going from the year 2000 to the future year of 2100. That steep decline is the occurrence of persistent, what we're calling mega drought. That is the near permanent establishment of dangerously dry conditions, dangerously arid conditions. So there have been some folks who say that this is too extreme, but we've been in an extreme drought period, as all of you know, for something more than a decade, something almost like 15 years. So this is something all of you know from personal experience that it's happening. And the take-home from this study is that it's going to happen and it will continue to exacerbate into the future. So this is why I think that trying to recast our climate change research into research that can help decision makers, policymakers, businesses, corporations, people who are trying to increase the profit side of their ledger and reduce the liability side of their ledger. Science can deliver on all of this information. We do this work naturally. This is what we do for a living anyway. The change is that the work that we can do is not the work that we can do through federal funding through the government. Some of you may have heard that Lamar Smith just passed a bill that is now going to be sent to President Obama, where he's requesting a flat NSF budget, National Science Foundation budget, for now 10 years. So that means in real dollars, investment in all of sciences is going down. But targeted in that bill, and if you want to see, I wrote a Huffington Post piece on this a month ago. Just Google my name and Huffington Post and you'll find it. What was in that bill was a targeted slashing of climate-related research. 10% from NASA and 12% from NSF. But it guts the kind of work that I've just been telling you about. That research will effectively stop. So there's a time when we really have to think about, what is this worth to us as an economy, as a nation, as a people, and to arm ourselves with the best information to make the best choices forward. One last point is that if you just take the biggest possible 30,000-foot view on this, is that the best way to look at climate change is that it's like an additional tax imposed by nature on our desire to extract an economy from nature. That tax is equivalent to about 1 to 2% of global GDP. For the US, in a proportional sense, it works out to be, if we have an $18 trillion budget, it works out to be about $180 trillion and multiples of that. And just to put that in context, Hurricane Sandy was $65 billion. So Hurricane Sandy was roughly 50% of this kind of number that we're talking about. So it makes sense. We actually have some personal experience with it. So I would like to wrap it with the notion that, or the suggestion that climate scientists are very actively working on trying to find these solutions, trying to find the best ways forward. I think our best way of looking at the future is by arming ourselves with the best information from the best places. We established the Center for Climate and Life to deliberately go after this particular initiative. But really, there are many such groups around the nation, around the world, that are trying to do a similar thing. And I'd wrap on this final statement, which is that Sherry Rowland, who was one of 3 authors who discovered the cause of the growing ozone hole back in the 70s and 80s, Sherry Rowland was given a Nobel Prize for that discovery. But in the course of doing this, he became very frustrated that once he had established the science so perfectly, the case had been made so clear that even back then they found some resistance. Looking back on it, though, the Montreal Protocol and the amendments after that actually established a lot of action that allowed us to actually make a very good course correction decades ago, so that now the ozone hole is repairing itself. we've turned the corner. Last year we turned the corner. The ozone hole is starting to get smaller and smaller. This is the success story in environmental policy, and is the success story for scientists. And we have the same challenge ahead of us now. It's many times bigger than that. But I have to believe that with the brain power that we have globally, but especially in this country, that we can absolutely do something, particularly since it's tied to our bottom line. Thank you very much. I was on time? Yeah. Okay, I'm willing to take questions. Can you please state your name and don't say anything until you have a microphone?
My name is Don Baker from Washington, D.C. Isn't the issue we've really got is the inability, it appears, in our political system to make long-term judgments and long-term investments? This morning, the professor was talking about Thomas Jefferson and the investment in the Louisiana Purchase. And in one issue after another in this conference, it seems to me we have some answers, but we can't seem to mobilize to deal with invest in the long-term problem. Do you agree?
Absolutely. I mean, you clearly put your finger on the number one problem. And my response to that would be that, again, what we've failed to do in the science community is to make our work relevant to that bottom line. Because I do think that when our nation or when our policymakers are faced with very compelling evidence that it's going to impact people's bottom line, that leads to action. And the reason why I'm strengthened by that is that that's exactly the tack that was taken for the Montreal Protocol. The story of the Montreal Protocol is that actually the scientific evidence came up, and within just a few years, that UN group got together and penciled out the initial draft, which then led to the subsequent amendments that put us on this road to repair that we are on now. So I think that we as climate scientists, but we as policymakers, we as business leaders need to work together rather than fighting amongst ourselves. I really think that's the most promising aspect for me. I mean, right now I'm spending a lot of my time talking with business leaders. It's a very different group for me. But I live in New York, and there's lots of business leaders in New York, and they like the message, and I think it's an empowering one, which is that they want to be part of it. So I was talking with the head of the International Chamber of Commerce just last week on this, and he assembled a group of 15 people, Terry McGraw, for those of you who may know him. And he's an enlightened businessman. He knows what's ahead, and he wants to know, how can I get ahead of the curve? How can I make wise decisions for me and my group and my nation and my global corporations based on the knowledge that you have? And it's incomplete knowledge, but we can give him that knowledge for sure. Yeah. Well, thanks for listening. Any other questions? Please.
Hi, I'm Griffin Hampstead. I'm a Bezos scholar here from Knoxville, Tennessee. We saw a lot of numbers, and there's no question that it's getting hotter. So my question is, what does that mean for the human species? Are we going to have to adapt? Is there going to be, like mass extinction from the heat? Is there going to be mass migration? What do you think the future of the human species looks like if the planet continues to heat up at this rate?
It's a great question. So I'm an optimist. I will hand up, I'm an optimist. I do believe that we're smart and we'll do the right thing. Maybe kicking and screaming, but we will do the right thing. There are very few aspects of climate change that are indeed killing, that are really indeed threatening. One is really gruesome, which some of you may not know about. It's actually the dew point. Temperatures in the interior parts of the continents become so warm and so humid that they exceed the dew point of our ability to evaporate. And so if you're outside and exposed, which luckily we're here in air conditioning, but if you work for a living outside, you die. You actually die living outside. So that's, that impacts actually a big chunk of this nation. There are parts of the country in the Midwest that become unbearably hot and humid. But that's another story. We found ways around that. My immediate concern is this fast brain, slow brain conundrum, which is that we know, probably everyone in this room, regardless of where you sit politically, probably says, yeah, we really ought to think this through and come up with the best way forward. And yet, we have this very reactive way of responding to it. We're leaning on our fast brain in the end when the crisis hits. And what I find empowering for myself, or what lets me stand up on these stages time and time again, is that it's a very human message, and it's something I know we can do. We just have to pull together. And it means that a lot of people have to step up to the plate who haven't stepped up before. And that's business, it's youth, it's everybody. We've got some hands. Please, Stanley.
Hi, Stanley Kritzik from Milwaukee, Wisconsin, where we haven't had a 90-degree day since last September. That's a political plug. It's one thing to deal with climate change over the next 10, 20, 30, 40 years, carbon and so on and so forth. But from a practical standpoint, you're not going to get anyone to, except maybe you, to seriously worry about that wobble that the Earth has,
Right.
which is going to be 5,000 years, and we're all going to be cooked then,
Right.
if we're around.
No, you're absolutely right. I will add that, and someone wants to chime in on this, I'm sure. There's a U.S. senator who actually responded to a U.S. Senate hearing on climate change, that he critiqued the climate scientists. So imagine me, it wasn't me, but imagine me in front of the senator. The senator said, well, Dr. Scientist, you haven't included orbital forcing in your climate models. And isn't that the pacing of the ice ages? Yes, it is, sir. Well, therefore, aren't you missing something awfully big in your climate models? And then, of course, he had to say, no, it wasn't, and explain why, and waste 15 minutes of valuable time having that discussion. But you got it already, so that's great. Please. Yep.
I have two questions, Nida McLemore, and you can answer either one. One is the geopolitical stability issue, and the other is I didn't quite understand the algae in the oceans and the breathing.
Great. Well, you'll be happy to know that the person who does know a lot about that, the woman who co-authored the study, is right in front of you. She's right there, Sonia Diarman. And yeah, so the ocean algae business is basically that the oceans are acidifying, and the ocean has, the way Sonia described it to me, is that you can imagine a landscape. For instance, here you see the dominant visual here would be trees in terms of vegetation, but there are bushes and there are ferns, there are grasses. Imagine that all the trees couldn't survive for some reason, let's say because of the beetle, for example, beetle infestation. What you're left with then is something that doesn't include forests, which would be very alien to all of us, and yet that's what the future would hold. So in the oceans, it's the same thing, except that its ocean acidification is leading to that change in the ecology of the oceans. And maybe, Sonia, if you want to add anything on top of that.
I don't have a mic. I'm happy to talk with you after.
Okay, great. And I'm sorry, I missed your first question. Yeah, so the geopolitical instability, I actually wanted to focus on that because that's actually another example I could have shown. We're all familiar with what happened in Syria, but the timetable of it is very curious because the cause of the instability in Syria was the depopulation of the Fertile Crescent in Syria to Damascus, to these urban centers where they became the urban poor. There were no resources or few resources to be able to support them. They became radicalized, and within a year, the civil war started. And a paper just came out in the proceedings of the National Academy of Sciences, I'll be happy to send to you, written by two colleagues of mine, actually three colleagues of mine at Columbia, basically making a very strong case that not only climate was an integral part of that instability, but that it also had a global warming, very likely had a global warming fingerprint to it.
I wanted to ask you if you had seen the documentary, The Pyramid Code, and that at one point the Nile was up against the pyramids and that the Nile has migrated 8 miles. and that it kind of correlates a lot with your diagram, that 35,000 BC, that it was fertile there, and that the initial two pyramids are potentially that old and are subtle energy structures. Did you-
I have not seen that movie, but it wouldn't surprise me because the course of the Nile has shifted many times. And in fact, there was a Nile equivalent in the Gulf of Sirte, which is in modern-day Libya. So there was another Nile, if you will, on the other side that was active at this time. Please.
Judith Barnard, I live in Aspen. When you talk to businessmen in New York, what exactly are you asking them to do?
I'm actually not asking them to do anything. I'm very humbly sitting in their very large offices trying to tell them that I think science is their best way forward. In other words, if they can't beat physics. You can't beat the planet. It's a losing bet. And they listen to that. And then they say, well, what can we do? And then then you've got them engaged, right? Then we've got a hook. And then we've got lots of things we can do. If they're a concern that's interested in agriculture, we have specialists who can guide them on this agricultural business that I just showed you with this agricultural modeling under different climate change scenarios. If they're a trade business, there are things that we can do that relate to trade. So we have ways of trying to find the best path forward to give them the science that they need, but it has to be science that addresses the global good. And I'm sorry. Yep.
What I'm saying is that these people really need to be led by the hand, and not just once, but steadily and regularly, because initially it'll cost them money.
Right.
And their shareholders will tell them they shouldn't be doing this.
No, you're absolutely right. So one reason that I'm encouraged by this, honestly, so Terry McGraw is chair of the International Chamber of Commerce. I had no idea. He represents 6 million businesses. It's a lot of businesses. So they sign off on a climate agreement. They're writing it now in front of COP21. And he wants to know what to say in that document. This happened last week. I don't know what to tell him what to say in that document, but I do know what should be part of that document. What I didn't know is that I knew that McGraw-Hill also owns Standard & Poor's. One of the interesting things is that Standard & Poor's now has an inclusion of climate as a liability exposure issue in credit ratings as of like a year or two ago. So that's a big deal. When you tie climate exposure to credit ratings, that'll get people's attention. Please. Is there other, am I missing? Oh, I'm sorry.
My name's
so
John Stroyer. I'm CEO of the world's largest responsible investment firm. I won't give you the name, but I want to address the question that was raised in terms of what people are asking corporations to do. And I would refer people to the United Nations Principles for Responsible Investment. We now have 1,400 large asset owners. These are the world's largest investors in pension funds worldwide that represent a little over $59 trillion in assets. And it is a growing and unified effort to ask corporations to set goals to reduce greenhouse gas emissions, amongst a number of other things, to try to solve these problems. As you and others in the audience have observed, our government regulatory framework is not capable of solving the problems. Supreme Court this morning denied passage of the bill to reduce greenhouse gas emissions from coal plants from the Obama administration. So I think what people can do and what is happening is a unified effort to ask corporations worldwide to set goals and targets to try to solve these problems, and ask corporations to live up to their role in society.
Great, thank you for that. We have one over here, and then you be next, please.
Hi, I'm Tara Montgomery. I head up health at Consumer Reports. I hear your call to action to the powerful people, but what can everyday consumers do or stop doing to be part of the solution?
Well, there are certainly a lot of things on the table, everything including personal choice, which is the one thing you have absolute control over. And then also where you put your money is another important decision. And that actually ends up being one of the more troubling ones, is what to invest in, what not to. But I also think that one of the things that was one of my most moving experiences in my adult life was marching in the climate march in New York. It was moving not because it was so big. It was moving not because it was such a diverse call of voices, but it felt like this was something that all of humanity was being part of. And so once it becomes that kind of a discussion, that we're all in it together and there are just a few holdouts, it becomes a very different power struggle because we are powerful. We basically run the world if we can unite our opinions, or if we can come up with a plan forward for how we want to see the planet. That said, that was a one-off event. But I did have the feeling after participating in it that it was really just one of several that will take form, not so much in marches, but in linked behavior choices, as some of the things that we've been talking about. Please. How are we doing on time? Oh, 5 minutes, great.
My name is Ahmad Hassan, and I'm from DC. My question is, as a profound scientist, what are some ideas that you have discussed with some colleagues of yours about stopping/preventing climate change from impacting our lives? And if there are, what are the burdens that are preventing this from being implemented into society?
Great question. To me, the biggest single problem is that we haven't come together as a global population to try to do something about it. There are a lot of self-interests that are fracturing our responses to it. So, again, I feel that a lot of our way forward has to be embracing how we want to see the world and not being happy with the world I just showed. So I think one of the best outcomes that can come from this is hopefully you'll all go to you'll talk to someone, you'll meet someone, you'll go to a party, and you'll remember this conversation we had today. And you'll take it up. You'll have the courage to bring it up with somebody, maybe even someone who may not share that opinion. And you'll talk to those people, and you get it to be part of the discussion. It has to be on the table. This is, I think, one of the biggest failings of how we initially talked about climate change, we meaning the broader scientific community and the media, is that it was basically a fear tactic. It was scaring people into this horrible future that becomes terrifying. And what's the worst way to stop smoking? Is to look at pictures of lung cancer. That's not the way you stop smoking. The way you stop smoking is, your friends come together and you have this sort of intervention and you stop smoking, or you come up with your own way of finding internal, strength to beat it. I think that was one of our biggest mistakes. I'm sorry. Yep. Mm-hmm. Go ahead.
Hi. Can you talk about some of the assumptions you have in the hockey stick? Because an earlier speaker today was arguing that in 10 years, solar becomes the cheapest form of power anyway. And so what are your assumptions that are driving that impact of greenhouse gases?
Right. So actually solar overtook, in terms of new electrons entering the global grid, solar took over fossil fuels last year. I don't know if any of you knew that, but the new electrons added to the global grid, renewables just barely beat out fossil fuels last year. So the revolution's already happened. I mean, the energy revolution is there, in my opinion. It's just a matter of time and policy options in terms of how that's going to ramp up. So I do think that renewables will take over. The problem is that our appetite for energy is so large that to replace it with renewables exclusively is just a massive undertaking. So, a complete redesign of the grid and a redesign of actually how we generate power. That said, I know we can do it, but it takes the political will to move forward on that. So I think we've turned that corner already, in my opinion. Now, to answer your other question, so there are various scenarios forward. There are 4 different scenarios in the IPCC about what the future might look like. The most aggressive one is called RCP 8.5, and that is basically warming that's equivalent to 8.5 watts per meter squared of additional heating due to greenhouse gases. That's when it was first being included in the experiments, it was thought to be this outrageously aggressive view of the future. And yet, that's exactly the trajectory we're on right now. We're on the 8.5 trajectory in terms of carbon emissions. The most positive emissions view is one that no one I've ever spoken to thinks is even is possible. And that's the only one that has a slightly capped warming and a decrease by the end of this century. So the world would have to be a very, very different place indeed for us to not have continued warming for the next century, which is exactly why we're here. You had a question, please.
Hi, I'm
Okay.
Sandy Starr from Lodi, California, and I'm a Bezos educator scholar here. And my question has to do a little bit piggybacking off of the panel before that talked about some of the water issues going on in California. But what are your predictions as far as climate change and water and those effects on agriculture in California? Because that's a big part of our economy there.
Right, so one of my colleagues at Columbia is Wally Broker. He's actually the person who coined the term global warming. And I was talking to him about this a little while ago, and we were having sort of a coffee conversation about what we thought was going to be, what's going to be the first sort of fingerprint of global warming other than just the steady warming. What's going to be the real tipping point or the thing that will get people's attention? I think it's water. So, I think it's certainly in my lifetime. One more question?
Hi, David Newberger. If renewable is now the cheapest form of energy we can create, does that open up the ability to capture carbon back out of the atmosphere? Because that's the big stumbling block, I understand, is the cost of doing that.
Right. That's a great question. So the challenge of our future is twofold. One is trying to decarbonize or reduce the carbon intensity of the global economy, and that's one that I think we could do tomorrow. If someone asked the question, if you could be czar, what would you do? That's what I would do. Is I would incentivize all we could to do renewables, and no one's going to be building power. No one's going to be building hydro. They're going to be building out solar and solar hot water heaters. So those are your biggest bang for the buck, low-hanging fruit. The second issue is that there's so much carbon in the atmosphere and there's so much momentum moving forward to stay on a carbon-burning trajectory that we will very likely have to have technologies to remove carbon from the atmosphere. Those are very much still in development. At Columbia, we had a few people who were working on that, and they all had their own different style, but they're all iterations on the same theme, which is this amine technology. It's a nitrogen-bearing molecule that they use for rebreathers to pull carbon dioxide out of our breath, and you can insert oxygen. That's how you can breathe underwater with no bubbles. It's like what the Navy SEALs do. You just do that in a very large way to capture the carbon. A big remaining problem is what to do with that carbon once you've done it. I mean, just to give you an idea, we're talking about filling large lake basins with either precipitated calcite, mineral limestone, securing carbon dioxide that was once gaseous, liquefying it, reacting it with, you can react it with basalt, for example, or peridotite, another rock type where it'll calcify. But that's a very hard thing. The reaction rates are pretty slow. So we have a team at Columbia that's actually looking into that. It's not to say that we can't do it, but it's something that we really should be working on. So luckily, we have some really smart people who are working on this. So I'm being told that I have 0 minutes remaining. Thank you very much.